thank you, Alexei, for this kind invitation to come here. I will give a survey of what our team has been done. This is a joint work that has been funded by the oil company here in Brazil, Petrópolis. And our target is to simulate the process of water flooding in the pre-salt reservoirs. So this was a recent discovery here in the southeast part of Brazil. It takes the coasts of the states of São Paulo, Rio de Janeiro, Espírito Santo, and Bahia. And the challenge here, it's a very deep formation. We are talking about 7,000 meters deep. So there's a carbonate here. So this is where the oil lies. It has a lot of CO2 there too. And the cap rock here, it's a rock salt. So it has a particular feature of a creep problem. Like, for instance, if you take a cup of salt and then you put your finger there, when you remove your finger, the salt is going to fill this hole. So this is the creep problem. We treat in terms of viscoelastic constitutive laws. So the challenge here, they came to us, the people there at the oil company came to us and asked, what's the law? We are talking about 7,000 meters deep. What's the role of, for instance, the geomechanics? Does the geomechanics is going to play a very strong role? Does it going to affect the production curves? So the three questions they pose us is these three ones. So this is the main target of this talk. What's the role? What's the role of the geomechanics on that? More precisely, is the creep of the rock salt is going to play an important role in the oil production? We know it plays a very important role in the case of the wellbore stability. When you are drilling a wellbore in a salt formation, the creep causes a lot of stability problems in the wellbore. The second one, which is the most important one, so this is basically what's the main target of coupling of the geomechanics, is the fault activation problem. So the problem is that there are many faults which are sealed. When you start pumping water, when you raise the pressure, when you also deplete the pressure, these faults can activate. So it can give rise to pathways for leakage of CO2 and for water too. So this is a very important question. No? So the question they are trying to pose is, what's the maximum pressure that we can inject so that the faults will not activate? So this is the second question, which is very important. And the third one that Professor Furtado has mentioned yesterday, it's the basic, it's the basic integrity of the cap rock. So we know for the case of the salt is a very good barrier. So the question is, for instance, if I want to inject CO2, does the CO2 is going to be trapped there, or it can activate faults, and this fault is going to cause leakage of fluid. So these are the basic three questions. I will say a little bit of history here. So the first basic model for single-phase flow for a poroelastic media was developed in the 40s by a Belgian guy named Biot. So the difference here, we are talking here about single-phase flow for poroelastic media, and incompressible fluid, and the rock matrix has also incompressible grains. So the difference here is that the flow problem here is going to be coupled with the volumetric strain. This is the volumetric strain, which is measured in terms of the displacement of the solid phase. And this system here, which is coupled with Darcy's law, is going to be coupled with the system of stress balance in the solid phase. So this is the total stress, which is decomposed into two parts. One is the pressure in the fluid, and the second one is the so-called defective stress tensor, which is the more basic case. Is just Hooke's law. It's given in terms of elastic law. But when we move into the press salt, into the rock salt, it's going to change the constitutive law, and it will behave as viscoelastic or viscoplastic. So the system, so the basic PGE system is given in terms of these two main variables here. One is the displacement of the solid phase, and the second one is the pressure in the fluid phase. So this is the basic problem. So this is for a single phase incompressible fluid, and the rock matrix is basically it's composed by incompressible grains. So when you move the problem, when you change the problem, then you add the bulk modulus of the fluid and the bulk modulus of the solid grains, there is here one additional term. So this mass balance here, which in the previous case is given by this two term, we'll have this term here, and this M here is the so-called BO modulus, which has these two additional terms here. One is the bulk modulus of the fluid, and the second one, Ks, is the bulk modulus of the solid grains. And there's this parameter here, which is alpha, which is the BO parameter, which is the one minus the bulk modulus of the drained case of the rock matrix over the bulk modulus of the solid grains. So for instance, when the solid grains are treated as incompressible, this alpha here is just 1. So this is the additional terms which appears in the mass balance, and this arises from the constitutive law for the M. M is the so-called fluid content. It's the product of the density times the porosity phi, and it's given in terms of this constitutive law. So this is the problem that is a very classical problem for a single-phase flow, slightly compressible linear fluid in a poroelastic solid. The question is how can we just extend this formulation for the two-phase flow problem and for the three-phase flow problem? For the two-phase flow problem, the problem is coupled. So this is the previous system. So this is the previous system here. This is the previous system here, so it's an elastic law here. So this is the equilibrium problem with the stress tensor here and the pore pressure here. So this is the mass balance now. It has the classical pressure equation here with this term here, which takes into account the volumetric strain of the solid phase. This is going to be coupled with Darcy's law, and there's an additional saturation equation for the water. We are talking just about the case here of two-phase flow. And the main difference that the porosity is now a transient variable because the system is compacting. So the difference that the porosity lies inside the time derivative here, where in the rigid case it lies outside. So this term is in blue here. We are going to treat this in terms of the M. Okay, so M is the product of the density times the porosity, which the fluid water fluid content, and this is the new term which changes the saturation equation. And the pressure equation, now this M, which is the BO models, we need to replace M, the BO modulus of the water and the oil, by the so-called equivalent BO modulus, which is going to change with the saturation. So this is the additional term here, which just appears in the pressure equation, the total balance equation. So to get this law here, it's very simple. We just write the constitutive laws for the water content. We multiply it by the saturation. We just write for the oil, and and then we sum up, and then we just ended up with this relationship here, which is for this equivalent M here, which is basically the weighted average problem in terms of the saturations of the water and oil. So this closed the system, so this gives rise to the so-called fully coupled formulation for two-phase flow problem in a poroelastic media. So this is basically this first system here. It is the poromechanical system. It has an equilibrium. I'm just dropping the gravity terms here, but if you have the gravity, it's going to be a rho g here. So this is the split of the total stress tensor of a pressure in the fluid and the poroelastic term. So this is a total mass balance problem. So this is Darcy's law now, and K is going to change with the porosity. And this system is going to be coupled with the saturation equation with these two new terms here, where the porosity is changing with time. So this formulation has been used a lot in soil mechanics, in many problems, but for the petroleum engineering, it didn't go well. The difference that most companies have one simulator for the flow problem and a different simulator for the geomechanical problems. So they don't want to spend a lot of money in building a new simulator with all things coupled. So they want to build interfaces and do exchange terms with these two simulators. So this is one of the drawbacks that the classical formulation, the fully coupled formulation for the hydro-geomechanical problem didn't stay along strong in the oil business. And the difference that this formulation also imposed the same time scales for the geomechanics and the flow problem. And usually the meshes for the geomechanics are different from the meshes of the flow problem, because the meshes of the geomechanics also take into account the surrounding rocks. So usually, for instance, in the case of the pre-salt, we have one mesh for the flow problem, and the mesh for the geomechanical problem will also take into account the side burden, the side burden, under burden, and also overburden. So then usually the meshes for the geomechanical problems are larger than the meshes of the flow problem. So this is the difference why people have been using the so-called iterative couplet formulation. What is the main issue? That we have to just eliminate this term here, which is the volumetric strain, which is the divergence of the displacement field. We'll take the trace here, we'll take the trace in the stress decomposition of the total stress, and then we just eliminate the volumetric strain in terms of the total stress. So for instance, if we do that, we just ended up with this formulation, which basically it's a staggered formulation. The first one is the transport equation, which has this term here, which is the water content, is the product of the density times the porosity. So this is going to be coupled with a pressure equation here, a parabolic problem, which has a total compressibility now, which comes from the compressibility of the fluids. So this M here, it takes into account three compressibilities. One for the bulk modulus of the water, the other for the bulk modulus of the oil, and the bulk modulus of the grains. And this term here, it's the bulk modulus of the drainage of the rock itself. Okay, so this is the total one. So this pressure equation here, this parabolic problem, has an additional source term which comes from the total stress. And this is going to be coupled with the geomechanical problem, which is in the simplest case, in the poroelastic case, is just this term here. You see that the pressure gradient will behave as a gravity term here. So you solve this problem in terms of an iterative coupling. You solve the flow problem with the source term here, with the source term here, and you solve also the geomechanical coupling with the source term that comes from the pressure gradient. So then when you move, so this system here can solve it in a larger domain, which also includes the surrounding rocks. And then you do this in a iterative fashion. When it stops, you give a certain tolerance, and then you solve this saturation equation explicit in times. So we are basically using IMPA's algorithm. This system here, it's solved in terms of an iterative fashion using implicit Euler, and the saturation equation is solved explicit in time. So the meshes for the geomechanics. So this is a typical picture of the pre-salt. It has the rock here with the oil, and it has a saline dome here. So these are the mesh for the flow problem. I'm just showing here in the 2D case, but we are now working on the 3D. We have these meshes here, which will solve the flow and the transport problem, and the surrounding mesh also, which has a viscoelastic constitutive law for the saline dome, will be solved for the geomechanical problem. When we are in these elements here, we have to add this source term here, which comes from the pressure gradient. But for the surrounding elements, the source and the variational formulation will come in terms of the Neumann, the traction boundary conditions. So this is basically what we solve. So this is the picture that they gave us. We are going to solve the flow problem here, and we are going to solve the geomechanical problems in this whole area here, which has the side burden, under burden, and also overburden. When we move from here to here, we will now pursue work with a viscoelastic constitutive law for the stress tensor. So we have to solve this problem. We have to solve this problem for different realizations of the parameters here, which are the bulk modulus, the Young modulus, the permeability, initial porosity. So we are going to solve this problem in a staggered fashion. So the staggered fashion, the first one is the flow problem. We solve that in terms of a mixed finite element method. So this is the formulation in terms of velocity and pressure, and this is the source term that comes from the geomechanics. So we are strictly in the parabolic case. So for this case, we are going to use piecewise constant approximations for pressure and the normal component of the velocity field in the middle of the edges of the elements here. But since the pressure is discontinuous, it's a piecewise constant formulation. We can use, for instance, Euler scheme, and we can do a static condensation. We can just eliminate the degrees of freedom of pressure and plug here in the variational statement of Darcy's law. We plug this here, and then we can assemble a single matrix for the Darcy velocity field. We solve that. So this is positive definite. We solve for the Darcy velocity, and then we get the Darcy velocity at the normal component at the edges, and then after solving for the Darcy velocity, we post-process the pressure. So we keep track of, for instance, the mass balance at each level here. For the saturation equation, we have this terminal here. So we use the product, the time derivative of the product. This gives rise to two terms. One is this term here, and there's another term here which plays a role of a source term. So we have a different time scale here, because this term changes with the porosity phi, and it changes on a much coarser time scale compared to the time scale of the water flooding problem. So this is a typical picture where we can use splittings here. So we use two splittings here. One is the first one. We solve the first problem, the predictor problem, by just dropping the source term. So this is the same problem for a case of a rigid media. We can choose your favorite method here. We use a higher order finite volume scheme for that. And for and then we put a corrector problem by just exploring the difference in these time scales here. So this time scale in red is much faster than the time scale in blue. So we can freeze this time scale here. We just use implicit Euler scheme here. We take integration in time, and then we take exponential, and we just end up with this relationship here, which is the second step. It's the corrector step. The first problem, the predictor problem, we solve in terms of the finite volume method, and then for each smaller time step we are solving with the finite volume method, we do a corrector step to solve for the geomechanical coupling. So this we have IMPs, we have coarser time steps for the flow and the geomechanics. We have smaller time steps which are constrained by the CFL number, and we have one mesh for the flow, one step for the finite volume problem, and the second step for we can do one analytically correction using this term which takes into account the geomechanical coupling. The second one, so this is the predictor problem, which is solved by a higher order finite volume method, and we can also use strung, which is the higher order splitting. It solves on the half of the time step, it solves the predictor problem. Then it gives a full correction of the geomechanics and solve it again with the half of the time step. So we have just implemented these two cases. One is the Godunov splitting, and the second one is the strung splitting, just to exploring the difference in the time scales of the geomechanics and the water flooding problem. So to solve for now, we solved the flow problem with mixed finite element methods. We solved the saturation problem using this splitting method using finite volumes and strung splitting. And to solve for the geomechanical problem, when we move to the rock salt, we need to take into account this strain, this viscous strain here, which is a power law, which has a power law behavior in terms of the shear stress. This S here, it's the deviatoric part of the stress tensor, and it's the one which causes creep. The creep of the salt is just due to shear stress. When you shear that, you have creep, but it doesn't creep with the volumetric stress. So this problem is going to be solved with a mixed finite element formulation. This is the classical one. This is the B-bar method now, which has been developed by Tom Hughes, and we just integrated the flow rule. So this is the flow of the viscous strain at each Gauss point. So in doing that, we have to just assemble this tangent matrix here. For the elastic case, it's just a C. For the viscoelastic case, it has to be updated. And we solve this problem in terms of the semi-predictor corrector scheme. So this is the first step, which is the predictor problem. It's just elastic case. For the viscoelastic case, we do, so this is the constitutive law. We first do a linear elastic step, and then we do the corrector step to reach the curve here, stress strain curve. So this is the corrector step is doing at which Gauss point, where we solve for this von Mises stress here, and this is the final algorithm. So we first solve for the elastic problem, we solve for the viscoelastic problem, and the main issue here is just to assemble this stiffness matrix here, which is non-linear now in this case here. So this is the final. So this is the final algorithm. We have the flow problem, which we solve with iterative coupled with the geomechanical problem. The geomechanical problem is solved in these meshes which take into account the surrounding rocks, and we solve also the saturation problem using this strung splitting or Godunov splittings. So this is the benchmark. What we have. This is the injection well. This is the production well. So we are going to try to calculate, also study. So these are the parameters that the oil company gave us. So these are a lot of parameters here. So there is Young modulus, there is the viscosity, there is the parameters of the rock salt, Young modulus of the alite. So there's two types of salt there. One is the alite, and the second one is the anhydrite. This has a stronger creep than this one. So these are the typical Young modulus for these two salts that they gave us. And we have to take into account, we have to solve the problems with boundary conditions in the far field. So this is the reservoir, and this is the surrounding rocks. We need to place these boundary conditions here in the far field. So we have to do a cutoff of the far field. So we solve the problem with different places of the boundary conditions until we just reach a point where we feel that the effect of the boundary condition will not change too much the flow and the transport problem. So this is the first solution. We see that the finger is moving here with the von Mises stress in the rock salt here. So this is for the elastic case, and this is for the viscoelastic case. So for instance, in the viscoelastic case, you can see that there is a relaxation of the stress. So it's a typical creep problem. No? You fix a strain. When you fix a strain, the stress will relax in time. It's a typical behavior of the viscoelastic problem, and this is the finger grow with the von Mises stresses, and this is the production curves. So this is for the rigid case. We are pumping here 300 meters per day. So for instance, in the rigid case, it goes into the breakthrough. So it goes down when the water reaches the production well. So this is with the elastic case. It has this compaction drive phenomena here. So the red is for the elastic case, and the green is for the elastic case, and the red is for the creep case. So there's a small difference because the creep will decrease the stiffness of the cap rock. So one of the nightmares of this problem is to lose integrity of the cap rock. So here is not too much. The difference is not so high. When you put more discharge here, now we are pumping 500 cubic meters per day. The difference is a little bit higher, but not too much. So this is the effect of the creep. The second one, what they asked us is, many softwares have done the so-called one-way coupling. So this one-way coupling, you drop the source term in the flow problem. You just have the flow problem enters in terms of a pressure gradient in terms of the geomechanics, but the geomechanics, you just drop this term, and then you solve this flow problem here. So this is called one-way coupling. So the flow affects the geomechanics, but the geomechanics does not give the source term for the flow problem. So the so-called one-way coupling, you just drop this source term here. The difference in these two is very big. You see that there is this is the one-way. So this is the one-way coupling in the left. So this is the two-way coupling in the right. You see that the finger has reached here, and in the one-way coupling it didn't reach as well. So the difference that when you look at the breakthrough curves, so there's a difference. So the difference is that this is in the rigid case. So this is the rigid case here. You are pumping 300 30, so it goes in the region until the water arrives at the production well. So this is the two-way. It has a earlier peak here, so this is the breakthrough of the two-way, and this is the breakthrough of the one-way. So there's a difference in that. We didn't see a lot of difference in the solution in the Strong and in the Godunov splittings. And we, how much time I have, Fred?
You have 10 minutes.
10 minutes, okay. We saw that the splitting error in this case is not so high. We use this error analysis, which was in the book of Levesque, and we see that the splitting error is only high provided this quantity here is very high. So we plotted this quantity, and we didn't see a lot of difference using a first-order splitting or a second-order splitting. They gave us very, very similar relations. So this is the breakthrough curves in terms of the, so this is the influence. So these curves here show what's the influence of the BO models. So this BO models, it takes into account the compressibility of the fluids and the compressibility of the solid grains. For the case where these bulk modulus are very high, this guy is 0, which gives these curves here. So this is the two-way curve, and this is the one-way curve. When you plug these parameters here, this is going to also affect the breakthrough curves. You see that the compressibility of the fluids will lead to a decrease in the breakthrough curves. So these are the two curves, two-way and one-way, for the case where this parameter here is 0. So this Kf and Ks are very big, which is the case of incompressible fluids. And these are the two curves for the compressible case. And we are going to reach down now the main issue of the lecture. It's the case of fault activation. So this is the main problem here. We need to do accurate computations of the stresses to just make sure that the faults are sealed. So the first thing what we have to do is to estimate what's the first stress, what's the stress tensor before we do this flow problem. So this is the so-called the in situ stresses, which is due to the gravity term. So I have to just estimate what are the stresses in the carbonate due to the weight of all of the overlaying rocks. So we have to add the weight of the water plus the weight of the post-salt and plus the weight of the salt, and this gives you the difference. So this is for the fluid part. So the fluid part is just the gravity term here. So this is the total stress. The difference of these two will give you what's the estimate of the vertical effective stress. So we have to just estimate what's the vertical effective stress and also the horizontal stress. So to do that, we take into account the gravity. So this is the density. So this is the estimate of the total stress. We take the density of the rock, and then we multiply it by G. So this is the increase of the total stress per meter. We do the same thing for the water, for the oil here. And this is this is due to the fluid, and the difference in these two will give what's the change of the vertical effective stress per H. So when you just increase H, so this is a linear behavior with H. So this gives you this relationship here, which is how the vertical stress is going to change with the depth. And to also estimate what's the horizontal stress, we consider the fixed, the plane strain model. We can do this to estimate what's the horizontal stress in terms of the Poisson ratio. So by doing that, we have two scenarios here. One is the fault activation when the horizontal stress is higher than the vertical stress. So this is going to cause a slip that this part here will climb. You know, this right part of the fault will move up compared to the bottom part here. So this is called a transcurrent reverse regime, where the sigma 1, which is the horizontal stress, is higher than the vertical stress. So this is a typical problem which can happen near the injection well. And the normal one, which is this one, is when the vertical stress is much higher than the horizontal stress. So this is going to cause a slip which looks like this. So basically what we have to do is to compute what's the principal stress. We need to compute what's the eigenvalues of the stress tensor. It's a symmetric tensor, so these eigenvalues are real values. So when we are in the normal regime, which is here, so this is a typical problem which happens near the production well. The pressure is going down. We are depleting, so the force will transfer from the fluid to the solid matrix. This vertical strain here is going to move to the right, higher than this stress here. So this more circular will touch this more Coulomb failure surface, and this is the case where the faults which are seated can also activate. And the second case is when we are near the injection well, so the stresses go down because you are just injecting there. So the pressure goes up and the stress goes down, and this more circular here moves to the left. When it touches this more Coulomb failure surface, you can have fault activation due to this mechanism here. So they ask us to build scenarios for these fault activations. So we compute the vertical stress and the total stress. So it's much more. So this is the injection well here. This is the production well here. The compression is much higher in the nearby the production well. When you move forward, so you see the two stresses here. So this is the vertical stress in the red one, and this is the horizontal stress. When you move forward, they are very separated nearby the production well, and they start to get very close in the injection well. So this is the ratio of them, how the ratio of them moves in time. So this is with X and how it evolves in time. And for the case of the production well, we are in this picture here with the sigma 1 here moving to the right much faster. So the chances that the fault is going to activate is that when the sigma 1 here moves very fast in the right, so this part of the shear stress here can touch this more Coulomb failure surface. For the other case, it's going to move to the left, and it's dangerous to have also activation there. So the time is over, right? Okay, I was going to talk about the gas phase. We have just extended the model for the three-phase flow problem, but I will talk about this in a different lecture. So the conclusions is that we believe that we have a right formulation to capture the main targets here, which is use this staggered scheme, solving the flow problem with mixed finite element method, solving the saturation problem with these types of splitting. We try both splitting, the strong splitting and the Godunov splitting, and we solve the geomechanical problem with the rock salt with the creep there. And we are now moving to solve the problem in terms of these three main issues. What is the effect of the rock salt is going to take? It's going to have upon the oil curves. What is the dangers? What's the maximum pressure we can pump water so that the faults will be seated, will not activate? And the third one, what we are starting now rather, it's to just study integrity of the cap rock. Okay, thank you very much.
Hello.
Thank you.